Our first speaker this morning is AnnabellaYang, who comes to us from UC Santa Barbara. Annabella has been working this summer with Meng, and she will tell us today about her project, Environmental Dependence of Stellar Populations in Galaxy Groups and Clusters at Redshift 0.1.
Thank you, Gwen, for the introduction. So I'm happy here today to talk more about the environmental dependence of stellar population. So studying the environmental impact of stellar population and galaxy evolution is significant in gaining insight into the history of the universe and comprehending how galaxies are formed. So a lot of study has been done, followed by Alan Dressler's famous morphology density relation, which connects galaxies' morphology to their environment. Alan Dressler is also a staff member here at Carnegie, and the plot on the right-hand side is a plot from his 1980 paper that compares the population of elliptical, spiral, and irregular galaxies to the density environment. His discovery is that the irregular galaxies tends to live in a lower density environment, while spiral and elliptical galaxies tend to live in a higher density environment. Yet, it is still unclear whether galaxy quenching is more affected by the environment or the internal process. And how does scaling relations such as mass metallicity, mass age, and mass alpha enhancement differ in different environments? So Thomas got a large sample of galaxies and produced these three scaling relation plots that connects the velocity dispersion, which directly reflects the mass of a galaxy, to the metallicity, age, and alpha enhancement. By comparing such scaling relation plot in different density environment, he made this conclusion that galaxies on average quench their star formation earlier in denser environment. As you can see, he plotted the look-back time of galaxies in higher density environment and lower density environment. And as you can see, the 2 giga-year shift here is the time difference. So we want to take a closer look into the specific environmental factor, which are dark matter halo and cluster-centric distance. So this comes to our central question: how do dark matter halo mass and cluster-centric distance impact stellar population and galaxy evolution? Why do we care about this? So dark matter halo, why do we care about dark matter halo? So dark matter occupies 85% of the total matter in the universe. And as you can see this in this figure, the structure of dark matter impacts where galaxies live and form. So previous study and Meng's simulation indicates that there are some connections between the dark matter halo mass and the stellar population. So based on this reason, we want to study their specific relation. So the most direct way to study this is to observe and compare satellite galaxies in the same groups or clusters. Based on this reason, we chose 76 samples of galaxies from 7 different clusters around redshift 0.12. And we covers a wide range of halo mass from 10 to the 13.6 to 10 to the 15.2 solar masses. After after choosing the sample, we want to discover what kind of sample we are looking at, because we specifically want the red sequence galaxy. So we got data from the Sloan Digital Sky Survey, and we measured the aperture photometry of a circular region with radius 1.5. After measuring that, we plotted it out in the color magnitude plot of I-band apparent magnitude against the G-I color index. We then compared our color magnitude diagram to a color magnitude diagram in other literature, we find that all of our galaxies has really high color index and lies in the red sequence. Since we have really high color index, we conclude that our galaxies are old red quiescent galaxies that has no or negligible star formation activity. And we also see a trend here that the older galaxies are redder as what is supposed to be. So after knowing the basic property of our galaxy, we take a closer look into the data spectra. So the data is taken by Meng using Magellan LDSS3 in a multi-slit mode. And the spectra contains a blue part and a red part. We combine the spectra and mask out the overlapping region and some flawed data on the two edge. We then performed Monte Carlo simulation using a code called ELF developed by Conroy. This code allows us to generate parameters that we are mostly interested in, which are age, metallicity, alpha enhancement, and chemical elemental abundance of carbon, nitrogen, oxygen, magnesium, silicon, calcium, titanium, and sodium. After understanding the model we are doing, I plotted the model data on the right-hand side with wavelengths in angstrom against flux in arbitrary unit. The red lines represents the best fit model we get, and the gray lines on the lower bottom layer represents the original data. And the residual percentage is relatively small, so we conclude that this model represents our data fairly well. We repeated the same progress for other galaxies in cluster 1, and we conclude the plot from cluster 1 here of object 1, 5, and 6. So we can see their spectra are really similar, and we can also see similar absorption feature. The redshift is calculated on the left-hand side, and the redshifts are also similar as we expected. Similarly, we got the similar conclusion from Galaxy 2 that they also have similar feature and similar redshifts. After fitting the spectra, we have the result from the Monte Carlo simulation. So we plotted the corner plot of the parameters that we are interested in, including age, metallicity, velocity dispersion, and alpha enhancement, which we use mg to Fe ratio here. The contour represents the correlation between the parameters of this specific galaxy, and the red dot in the middle is the median value, and the arrow bar is 1 sigma arrow here. We can see in the posterior plot, a bell curve shape is shown. That means like our trials converge to a certain value. So after this calculation of median 1 sigma arrow, we can then plot the scaling relation plot that was similar to Thomas' 2010 plot. So on the x-axis is the velocity dispersion. As said, it represents the mass of the galaxy. And on the 3 panels from top to bottom is the alpha enhancement, the metallicity, and the age. We can see they are somehow correlated, but due to the limitation of data points we have and the large arrow bar you can see over there, it's really hard to get a precise relationship. So it comes to our next step. We will be focusing on refining the data reduction because that's where the most error comes from. And then we will also incorporate the red region of the spectra because we are only using 4,000 angstrom to 5,600 angstrom for now, but we will make this region much larger. And we will also be adding a larger sample of scaling relation plot into the scaling relation plots. And this will provide more robust evidence when assessing environmental dependencies. And our conclusion is that we've analyzed 5 clusters with an emphasis on galaxies that has high signal noise ratio. And our spectral modeling indicates redshift consistent with expectations for cluster members. And we observe general trends between galaxy velocity dispersion and stellar population. That includes stellar metallicity, age, and alpha enhancement. As we add more targets, we will further investigate potential environmental dependencies. Thank you guys for listening, and I'm open to any question. Yeah.
What?
Thanks. Very nice work. So I have a question about the MCMC modeling, and it looks like that the ages are all kind of pushing against the prior. So I just want to ask, is that a prior like the age of the universe, or is it some different number?
Yeah, we kind of set the prior as the age of the universe so that it does not go over the limit. And we also set the prior for like other parameters because like there are usually limits in stellar populations and stuff.
Yeah, thank you. And so is this maybe an interesting finding? Is this something you expected, that all of those galaxies will be like so old, they're kind of basically kind of as old as the universe?
That's kind of like our sample selection. So we select the galaxies to be red and old galaxies.
Amazing work. You can hear me, right? So you said that these 3 things correlate with the velocity dispersion.
Yes.
And the velocity dispersion is connected to the mass of the supermassive black hole. So can you tell us a little bit how the physics of the supermassive black hole connects to these 3 quantities? How are those 2 connected?
Let me go back to the slide. So just to clarify, the velocity dispersion we are using is the velocity dispersion of the galaxy. So it's not correlated to the black hole itself or the dark matter halo that we are looking at. So dark matter halo should be calculated before. So it's like different clusters have the different dark matter halo they live in, and that's where we get the dark matter halo mass. And the velocity dispersion is like the mass of each galaxy. So this is basically like the scaling relation of galaxies, not like clusters or dark matter.
Yeah. I mean, I can send you references. People have found that the velocity dispersion is really tightly correlated with the mass of the supermassive black holes. But I can send you some references.
Yeah.
So you mentioned that in your current the current work that you've done so far, you focused on, I think you mentioned a wavelength range of like 5,000 angstroms to 6,000 angstroms, is that right?
Yeah, 4,000 angstrom to 5,600 angstrom.
Okay, yeah. I was curious if there was a reason why you picked that specific wavelength range just to start out with, or if it was just if that was an arbitrary limit.
Yes. So oh, sorry. The reason why we choose that range of spectrum is like because we have a blue part and a red part of the galaxy. So we basically the red part is like harder in terms of data reduction, and it covers a wider range of wavelengths. So we are now focusing on the blue spectra, and basically that's the range the blue spectra covers.
Okay, that makes sense. Thank you.
Yeah.
All right, let's thank Annabella for next.